Hey guys, it's Af! I am Maria Shinsugido.
I'm Fraser Pilapil.
I am Cedric Taves.
Super CJ Tatagan.
Edgar Ramirez.
Sana Kayla Viva.
Without further ado, let's get started.
And now, let us discuss about the three main topics: drops, dynamic, and daisies. First is drops. It refers to the shape of water drops and fluid motion by J. Edgar and T. F. DuPont on 1994, where they represent different equations regarding to flow. And second is dynamic, which refer to the population and demographics. In this study, the authors uses foxes and rabbits in a way of stimulating a study through a computer. And lastly, DAISIES, which refers to the view of conventional biologists that the flower genes specify in such information. The author explained the vital role of the genetic flower growth as it does the flower on how to make chlorophyll, which is responsible in absorption of light to provide energy for photosynthesis.
The chaos teaches us that systems obeying simple rules can behave in a surprisingly complicated ways. But the world cannot be totally chaotic, otherwise we would not be able to survive in it. Our use of language to describe our world rests upon the existence of underlying simplicities. In fact, one of the reasons that chaos was not discovered sooner is that, in many ways, our world is simple. For example, the statement, "Foxes chase rabbits," makes sense only because it captures a general pattern of animal interaction. However, if you start to look at the details, they rapidly become so complicated that the simplicity is lost. Recently, a radically different approach has been advocated under the name complexity theory. Complexity theory theme is that large-scale simplicities emerge from the complex interactions of large numbers of components.
For today's lesson, we are going to tackle drops, specifically the shape of the water drops. The formation of the detached drops begin with the bulging droplets from a surface, the end of the top. It develops a mist which narrows, and the lower part of the droplets appears to be heading toward the classic teardrop shear. But instead of pitching off to form a short, sharp tail, the waist lengthens into a long, thin, cylindrical thread with an almost spherical drops hanging from its end. Then, the thread starts to narrow right at the points where it meets the spur until it develops a sharp point. At this stage, the general shape is like a knitting needle. That is just like touching an orange. Then the orange falls away from the needle, pulsating slightly as it falls.
Now the slip end of the needle begins to round off and tiny waves travel back up the needle towards its root, making it look like at the tough end, and it too detaches it as it falls. Its tough end rounds off and a complicated series of waves travels along it. In 1994, G. Eggers and T. F. DuPont showed that the scenario is a consequence of the equations of fluid motion. They simulated those equations on a computer and reproduced Peregrine's scenario. It was a brilliant piece of work, but in some respects it does not provide a complete answer to other people equation. It is reassuring to learn that the equation of fluid flow to predict the correct scenario, but that in itself doesn't help them understand why that scenario happens further. Insight into the mechanism of detaching drops has come about through the work of X.D. Michael Brenner, Sidney Nagel of the University of Chicago.
Population dynamics. The use of the phrase reflect a long tradition of mathematical modeling in which the change in population of interacting creatures are represented by differential equation. It is a constantly changing in size and demographic. New animals are born, old animals die. Other factor just like fire and other predators, all because of the populations and the change of interacting creatures, are represented by differential equation and even probability and
It's 1994. Joachim Megley, David Rand, and Howard Wilson of Warwick University set up a computer simulation in which large numbers of internet according to biological possible rules and try to extract large-scale patterns from the results of the simulation. The system of rules is to set up the model main biological influence at work. For example, if a rabbit is annexed to a grass, it moves to the position of the grass and eats it. And the second, if a fox is annexed to a rabbit, moves to the position of the rabbit and eats it. This defines that a example large-scale futures energy from the fine structures of complex ecological games.
The third and final example of mathematical category of nature that emerges from complexity is the number of petals of flowers. They form the beginning of that so-called Fibonacci series, in which each number is the sum of the two that precede. The numbers that arise in plants, not just for petals but for all sorts of features, display mathematical regularities. If you look at the giant sunflower, you can find a remarkable pattern of florets in its head. These florets are arranged in two interesting families of spiral, one winding clockwise and other counterclockwise. In sum, the number of clockwise spirals is 34, and the number of counterclockwise spirals is 55. Both are Fibonacci numbers occurring consecutively. The general arrangement of the main features of the plants is laid down as a primo deformed Fibonacci spiral shape from primordium. Successive dots arranged at the angles of 137.5 degrees to each other along a Titan 1 spiral that shown naturally falls into two families of lousy one spirals that are immediately apparent to the eye. Here there are 8 spirals in one direction and 13 in other consecutively Fibonacci number. We use a divergence angle that is a rational multiple of 360 degrees. You always get a system of radial lines. There are gaps between the lines in the primordial don't pack efficiently to fill the space efficiently. You need a divergence angle that is an irrational multiple of 360. In particular, in many plants, the rate of appearance of primordia can speed up or slow down. In fact, changes in morphology, whether a given primordium becomes a leaf or a petal, they often accompany such variations of genes theoretically affect the timing of the appearance of the primordia, but plants don't need their genes to tell them or how to space the primordia, since that's done by the dynamic.
Three examples from every different parts of science, each in its own way an eye-opener. Each a case study in the origins of nature's numbers, the deep mathematical regulatories that can be detected in natural forms, and there is a common thread, an even deeper message buried within them. The drop's dynamics in DAISIES nature is complicated. No, is in its own simple way simple. However, those simplicities do not present themselves to us directly. Instead, nature
leaves clues for the mathematical detectives to puzzle over to a fascinating game even to a spectator.